Okay, we're back. So I would like to introduce you Craig Lovell. Craig is a software architect and computer scientist with over 20 years of experience designing, building mission-critical applications in financial, biotech, intelligence industries. So he specializes in artificial intelligence and algorithms, holds the bachelor's and master's from Carnegie Mellon University. He currently works at the ArctosAI, a company that he co-founded to build natural language processing and text mining applications. So please welcome Craig.
Thanks, Yuri. My name's Craig, and welcome to the session on natural language processing. So NLP is the field within AI that's focused on programming computers to understand human language. And this has been a field that's been near and dear to my heart for a number of years. And as I put together the slides for this talk, I had a hard time constraining the focus of the talk, as one of the things I want to convey is actually how broad this field is and how much research there is in the different areas of it. And you can think of NLP systems as this giant iceberg. And at the very top of the iceberg, the part you can see outside of the water, is the big concept the system's trying to accomplish, whether you're summarizing documents, or you're doing search, or building a personal digital assistant. Those are the big ideas in NLP. And one of the things that I want to convey is how deep the technology stack is underneath those systems. So what we'll see as we get into the talk is that those big ideas are actually composed of many lower-level natural language processing problems, and buried in there, of course, are some machine learning algorithms and lots of good math. And actually, math, if you like math, you've come to the right place. Not in this talk, but NLP in general. So there's everything from linear algebra. If you're doing neural networks, there's calculus, of course, probability and statistics. Pick your favorite machine learning algorithm, combinatorics, numerical methods. There's all kinds of good math in it. And then mixed in with that is plenty of mundane stuff as well. So just dealing with different input formats, dealing with multiple languages, extracting text from different character sets and encodings. So what I'd like to do in this talk is to sort of take a slice through this iceberg at a couple of methods and look at the high-level NLP algorithm and then lower-level NLP techniques and methods that it's built upon. So those are some of the things that I want to convey. And also throughout it, at the same time, at a few places we'll stop and point to places where we say, well, how would we actually run this thing on Spark to achieve some scale? But this talk will be more an NLP talk than it will be a Spark talk, but I'm going to be pointing out along the way the places where you could do these sorts of things on top of Spark. Okay, so to start off with, let's take a brief whirlwind tour of the history of natural language processing. In 1950, the renowned English cryptanalyst Alan Turing published a very famous paper where he proclaimed that machines could think, or the machines could be programmed to show intelligence. And in that paper, he proposed that we ought to have a criteria, we ought to have an objective test that we can say that'll let us decide whether or not we think we've created a computer program that's intelligence. And the test that he came up with, which is today known as the Turing Test, is actually a natural language processing problem. It's, can you build a chatbot which can interact with a human, and if a human judge looks at the transcript of that chatbot, if the judge can't tell which party is the human and which is the computer, then we must have created something intelligent. And there have been other philosophers and thinkers in history that have equated the capacity for language with intelligence, including Descartes. But Turing was really the one that codified this in terms of a test that we can do. So some of the early work in NLP was on machine translation. In 1954, there was a system that translated a few sentences from Russian to English in the domain of organic chemistry. That was actually built on an IBM mainframe and programmed and executed by feeding stacks of punch cards into a machine. So think about that the next time you're going to complain about how difficult it is to debug a Spark transform. Just be glad you're not debugging a stack of punch cards. I would hate to build an NLP system in that. So in 1968, 67, Joseph Weizenbaum created a chatbot called ELIZA, which mimicked a psychotherapist. And ELIZA worked by doing simple keyword spotting in the input and would sort of take your words and throw them back to you in the form of a question. So if you said, I'm feeling sad today, ELIZA would say, well, why do you say you're feeling sad? Well, I don't think my mother likes me. Tell me about your family. So it would sort of take the words that it spotted in your text and throw them back at you. And so it wasn't very sophisticated in its internal methods, but it could actually hold a conversation. Sometimes later, the system Shrdlu came out from Terry Winograd, which was a virtual blocks environment that had a natural language interface to it. So in this system, if you can imagine this domain where you have a table and you have a number of colored blocks on it, and you could tell Shrdlu, put the blue block on top of the green block, and it would say, okay, and it would update its internal model of the world. And then you can say, where's the blue block? And it would say, well, it's on top of the green block. So, and this was, showed an actual limited problem domain, but something that you could put a natural language interface on top of to interact with it. So soon after that, these things started getting practical, and the Lifer ladder system was a system to actually build a natural language query interface on top of a database of US Navy ships. And so you could actually express a query in natural language, and the system would turn it into SQL, and it could actually execute some simple joins. So you could say, where's the ship that has a doctor that's closest to Havana? Or what are all the positions of the American cruisers? So this is actually a practical application of taking natural language and transforming it into a SQL, which is much more difficult for users to comprehend. So a useful application in this case. In the 80s and 90s, there was sort of a shift away from these grammar-based and lookup-based and rule-based systems and more into statistical techniques. And this corresponded with the rise of machine learning technology, and a lot of machine learning algorithms were incorporated into NLP in these years. In 91, the Loebner Prize was founded for the Turing Test. And that is actually a prize that's, I think it's up to 100 grand at this point for the first chatbot that can actually pass the Turing Test. And it goes on to this day every year, and they award sort of a consolation prize for the best chatbot. They actually use a panel of judges, and I think the best bot so far has maybe fooled 3 judges, but no one's done better than that so far. And then recently, of course, there's been some great leaps and bounds in NLP. So in 2006, IBM's Watson won Jeopardy using a question answering system and actually defeated human players. And that same year, Google Translate launched. And since then, Google's been adding languages and improving their translation capabilities along the way. And finally, in 2010, was sort of the beginning of the rise of the personal digital assistants, beginning with Siri, which was a project that started at SRI International and was technology that was acquired by Apple for Siri. So this shows you through a few milestones in history the progression of the scope and the power of these NLP systems. All right, so what makes NLP difficult? Text is really messy, and language is messy as well. So language is ambiguous. The classic example, I see the man on the hill with a telescope. Am I looking through the telescope to see the man, or does the man on the hill have the telescope? It's actually ambiguous. And to compound that, words actually have multiple meanings. So if you were to see the text Mississippi Bank in a text, are you referring to the bank of a river or a financial institution? And humans do this instinctively by understanding the context in which that appears. But that is actually a problem called word sense disambiguation in NLP, where people have tried to write software to distinguish between 2 senses of the word bank, or 2 senses of different words. And again, it's a contextual problem. So finally, if your system is going to process social media data, there's a whole new level of linguistic nuance and eloquence you need to deal with. But things like sarcasm, humor, and irony, very difficult for computers to understand, although people have actually attempted it. So if we were to take that iceberg view and drill into it a little bit, these are some of the problems that are very active in NLP. And at the top level of this stack, you see the big ideas and the applications that are being built. So conversational agents, sentence parsing, sentiment analysis, summarization, and all these things are built on top of lower level NLP methods. And so one of the things I want to convey in the talk is the breadth of this field is really incredible, because in order to build one of these systems in maybe the top 2 layers of this, you might have to build or incorporate several of the boxes below it to get to that point. And each one of these boxes is an active research area, maybe with its own suite of algorithms and even machine learning algorithms behind it. And if you start at the bottom, even tokenization, the simplest thing, right? So how do I take my text and just divide it up into words? It's actually a hard problem, and it's different by language. So especially if you look at Asian languages that use logograms, the tokenization or the association of different symbols together to form a word can actually affect the meaning of the document, the meaning of the word drastically. And even in English, there's plenty of anomalies too. So you just take something like a hyphenated word. Should that be 2 tokens or 1 token? What if the hyphen is dividing a word between syllables across lines? Should your tokenizer know to combine that into 1 word? Even things like tokenization are not trivial. And if you think you can just split your text on white space and go, you're likely going to run into some problems. So some of these other boxes, sentence detection is usually the first thing you do in a natural language processing pipeline. We'll talk about how pipelines work. Finding the boundaries of a sentence is an open problem. There are libraries, of course, that do it for you. Language detection, there are some of the earliest and most successful algorithms worked on distributions of trigrams of letters. So you can take a corpus of text across different languages and calculate the distribution of trigrams of letters, so 3-letter combinations that occur in sequence. And you find that each language will have a different distribution of trigrams in it. And so if you have a new document and you want to find out what language you think it's in, you could create a histogram of those trigrams in that document, and then you compare that with the histograms of the corpuses you have, and the one that it's closest to, you could decide it's in that language. There's actually other algorithms nowadays that need to deal with text switching languages midstream in the middle of a document. So if you're building a multilingual system, then you might need that brick in your system. Things like named entity recognition and concept mapping also bring a lot more meaning to your text processing. So concept mapping is where you have an ontology or a dictionary, and you want to recognize multiple ways of saying the same thing. So for example, say you're in the medical domain and you have a bunch of texts about the medical domain. You would want that concept of heart attack to be known as the same concept as myocardial infarction. This is important for search as well. So if you're doing a search and you search on heart attack, I would hope that I would find documents that had myocardial infarction in them as well. And you wouldn't know that unless you had built an ontology or a dictionary in that domain that will help you map those to the same concept. Named entity recognition is of course picking up on the proper names in the text, people, places, and locations, and those are often very significant topically to a document. So if you can perform named entity recognition as a way of doing feature engineering before you're feeding some machine learning algorithm, those are often very significant features. Lemmatization or stemming is finding the root of a word. There's generally 2 approaches to this. One is a stemming algorithm, which will sort of knock prefixes and suffixes off a word until you arrive at something foundational. So for example, the word swim, swimming, and swam, you've got 3 tenses of the same word. The ing form, it's easy. You can knock off the suffix ing, the gerund form of the verb, and arrive at the root of swim. But swam is a little different. There's nothing you can knock off of that'll get you to swim. So you need to use a lexicon for that. So there are various algorithms that combine lexical lookup to do stemming with algorithms that just manipulate suffixes and prefixes of words. And again, that's important because if you're looking at the topic of an article, you don't want swimming and swim to be represented differently in your feature set. They're really the same word effectively, unless you're really looking at sentence parsing and syntactic structure. So word sensitive ambiguation we mentioned in the first slide as well. That's where you're trying to distinguish what sense of a word is being used. We're talking about the side of a river or a financial institution for the word bank. So for the rest of the talk, I'd like to dive into 2 of these top-level boxes, namely clustering and sentiment analysis, and we'll show how those systems can be composed of these lower-level NLP components. So starting with clustering, Clustering is basically taking a bunch of documents and dividing it into groups of like documents by topic. And the first thing you notice about clustering is that, well, it's a machine learning algorithm that's been around for a while. There's lots of algorithms, actually. But they all work on the typical machine learning data set, which is a fixed length vector that's been cleaned and pre-processed, where each position in the vector is a feature. How the heck do you run a document through that? You could have documents of any different length that you're clustering together, and words, of course, are jumbled up in who knows what order according to the sentences. So how do you actually turn an unstructured document into a vector so that you could run a machine learning clustering algorithm on it? And that's, question? So no, we'll get into that exact thing on the next slide, but basically you need to represent the document as a vector of features if you're going to feed it into a machine learning algorithm. So the next slides will talk about how you actually take that document and you cram it into a vector. In this case, we'll talk about one technique called TF-IDF, which stands for term frequency inverse document frequency. So this is based on the idea that the more times a word occurs in a document, the more significant that term is, or that word, to the subject of the document. Unless that word occurs a lot across all your documents. So for example, if you go back to having corpuses of different domains, if you're processing text, say, in articles about cybersecurity, and you see the word malware pop up a lot, well, malware might not be a really significant term just because it occurs a lot in that document, because your whole domain is essentially about malware, and that term's going to occur a lot in all the documents. But if you were processing, say, a set of documents about medical devices or the healthcare industry, and the word malware popped up a lot in one document, that would make you scratch your head and say, well, that must be a significant word for what this document is. Maybe it's about malware and medical device software or something. So the idea behind TF-IDF is more mentions in a document means the word is significant, unless that word occurs a lot across all the documents in your collection. And so the way this is expressed in the math is term frequency is simply a count of times that a term appears in a document. And inverse document frequency is the number of documents divided by the number of documents containing that term. And so you can see that there's an interplay in this formula between the number of mentions and the number of documents that contain the term. So as the mentions increase in a document, term frequency increases, and as that number of documents contain that term increases, inverse document frequency is going to push that value down. So the idea is what you end up with is for a document, for a term, a score for how important is that term for that document in that collection of documents. So once you have this, you can actually create a vector of all the terms, and each document can be reflected as a vector where each position is a word or a term, and the value in that vector is the TF-IDF score for the term in that document. So obviously this could be a really sparse vector, right? So if you look at all the words across a corpus of text, it could be tens of thousands, right? And there are lots of tricks you can do, including some of the other NLP building blocks that we talked about on the last slide, to actually reduce that vector. So one thing is if you can actually use concept mapping or named entity recognition, rather than putting individual words in this vector, you can put a whole concept in, and that'll be a much more precise feature to put in your feature vector. Similarly, if the word swimming, swim, and swam are all in your document, there's no reason for those to be 3 positions in your vector because they're all expressing the same root word. So typically when you build a TF-IDF vector, you might stem the word first, and so you just put in swim. So there's ways to manage the size of this vector, but it's still going to be a pretty sparse vector, and there'll be a lot of zeros for words that don't occur in a particular document. And so one other thing to notice is that this representation of a document just completely throws out all ordering of words in context, right? It's just a big bag. It's called bag of words, literally. You're expressing a document as really a vector of the significant words or terms in that document. So now, finally, we can get to the point where we build a vector that we can then feed into another algorithm. And this is where NLP systems, again, tend to be composed of lots of lower level NLP systems. So a typical pipeline to prepare a set of documents for clustering, so you might start with something rather mundane, right? Just extracting the text, whether it's from an HTML page or PDF document or whatever your data source is. And then you would start with tokenization, where you then break up the document into words or terms. And then you might apply some other NLP techniques to make the features in your vector more precise and more expressive. So you could apply lemmatization and reduce the words to their root. That'll actually shrink your vector down. You could apply named entity recognition and concept mapping. So you can actually put positions in your vector for terms that are high-level concepts that are going to be very significant rather than just using individual words in it. And there's, of course, several different pipeline technologies out there for building NLP pipelines, and you can pick your favorite poison if you like Java or Scala or Python. There's several toolkits. And this is one of the great things about building NLP systems in this day and age, is that you can really compose these things very easily. So if you're starting a new NLP project tomorrow, you don't have to start day one and say, okay, let's write a tokenizer. Get somebody else's tokenizer. There's a whole bunch of them. Question? Well, Java is too. They're both running virtual machines, but yeah. Yep. I don't think so. I think the Python toolkits are quite fast as well. Yeah. And I think the bigger boost in performance is going to come when you distribute them. So it's almost like the performance within a particular VM maybe doesn't matter as much compared to the lift you're going to get when you actually distribute an algorithm. But I don't think there's a huge performance difference between. Yeah, when you parallelize them. Yeah, that's what will give you a bigger lift. So your NLP pipeline might start with tokenization, do part-of-speech tagging, lemmatizing to pick out the root, apply named entity recognition, concept mapping, and finally you can assemble a vector for each document, and then you can feed these vectors into, say, a clustering algorithm. So here's another cheap way to calculate TF-IDF. If you're building an NLP system and you're already indexing documents in something like Elasticsearch, Elasticsearch is built on top of Lucene, which is a Java-based full-text indexing and search library. And Elasticsearch and Lucene actually search by using TF-IDF vectors for determining relevance and closeness of documents and queries. So if you're not building a system where you need to index the documents, it's probably overkill to bring Elasticsearch in just to generate TF-IDF vectors. But it's very common if you're already building an NLP system and you're indexing and you're using Elasticsearch, you can actually let Elasticsearch do the TF-IDF calculations as your documents get added to the repository and indexed. And there's very simple REST calls where you can extract term vectors from Elasticsearch either at a document level or across an entire index in one shot. So this could be very useful if your architecture already has Elasticsearch in it. You can sort of get TF-IDF for free. And in this case, when you index a document into Elasticsearch, you're actually running a little mini NLP pipeline inside of Elasticsearch that's comprised of tokenizers and token filters. And so you can actually put some of these NLP algorithms behind those interfaces, and so that the stream of tokens that Elasticsearch will generate to index can actually have baked into it things like named entity recognition and lemmatization and that sort of thing. So this is another cheap way you can calculate TF-IDF. So finally, we come to some Spark, and now we can actually talk about clustering. So now we're going to feed our document vectors into a machine learning algorithm. In this case, this example, we can use k-means clustering, which is part of MLlib. And the interesting thing to note here is that k-means clustering is a generic machine learning algorithm. So it knows nothing about NLP. All it's doing is say, give me all your vectors of features, and I'm just going to cluster them all by Euclidean distance. So this is an area where the final step in this process really has nothing to do with NLP. All the NLP was doing essentially was giving you feature engineering to construct those vectors to feed into the machine learning algorithm. So k-means clustering, the way it works is you pick your number of clusters ahead of time, and you can seed it with, say, if you're doing 10 clusters, you could pick 10 random documents, and you say, okay, those are the new centers of my clusters. And then for every other document, you take the vector, the TF-IDF vector for that document, and you compare it to the centroid of the cluster. And in k-means case, it uses Euclidean distance for this. And so these are, remember, you're representing a document as just a vector of numbers. So there's some very simple distance metric you can use here. And then you assign that document to the cluster, which produces the smallest squared error or squared difference in the, according to your distance metric. And then when you add a document to the cluster, you update the mean vector for that cluster. You actually take the average of the vectors, and that represents the centroid, the new centroid of the cluster, which will shift a little bit every time you add a document into it. And you repeat this. So you distribute the documents, the vectors, throughout these clusters, picking the closest cluster for each one. And each time you add a vector to a cluster, the centroid of that cluster shifts a little bit. And then after you've made a pass through all your documents, you take those means and you can start them off as a seed for another pass of the algorithm against those, rather than starting it with random documents. And so you finish and you continue these passes until you either minimize the squared error across the clusters, or until you've done some fixed number of passes. And then it turns out in Spark, this is trivial to do in just a few lines of code. Again, all the work was in constructing the term vectors to feed into this algorithm. Once you have it, very simple to create an RDD from that and feed it into, the first thing you need to do is normalize the vectors. The reason you do this is if you are clustering documents and some are little snippets of text and some are giant 50-page documents, naturally the larger documents are going to have higher term frequencies because they've got more words. So there's more likelihood that those words are going to occur multiple times. So the way you compare a large document with a small document in terms of the subject is you have to first normalize the length of the vectors, and then you can use something like Euclidean distance. And k-means uses Euclidean distance, but a lot of algorithms, when you're comparing documents and term vectors, will use what's called cosine similarity, which is where you can think of these vectors as points, and it might be easiest to think about it if you only have two terms to deal with. So let's say your vector only had two positions for cat and dog. You could plot those on an XY graph. How many dogs did you find and how many cats did you find in terms of TF-IDF? And that'll give you two vectors from the origin. Cosine similarity is where you take the angle between those vectors and then you take the cosine of it. The reason you take the cosine is because that angle, since these are all vector components with positive numbers, will all be in one quadrant of your plot, of your graph, and therefore the angle between them is at most 90 degrees. And cosine from 0 to 90 degrees will go between 0 and 1. So it gives you a convenient distance metric to take the cosine of the angle between two vectors and use that as a similarity score or a distance vector. That turns out that approach actually extends into multi-dimensional vectors beyond two. So you can actually use cosine distance very easily, which is actually used in things like search as well to compare documents. And there are other clustering algorithms as well. So k-means is an example of a generic machine learning algorithm, but there are other clustering algorithms that in NLP that focus on clustering documents. So there's one popular one called Lingo, which is a part of the Caret2 clustering engine in Java. And that works by taking the TF-IDF vectors for all these documents, and you stack them up one column per document. You get a giant matrix, and you do a singular value decomposition against that, which is a linear algebra algorithm that actually teases out a set of relevant terms and a set of documents, and then a relationship matrix in between them. And so by doing that, you can extract out a set of basis vectors using singular value decomposition that you then use to form cluster labels, and then run all your documents past it with a distance metric to pick a cluster for each document. So that's a more involved algorithm that's actually specific to NLP and not like a generic algorithm like k-means is. All right, so that's an example of clustering on Spark. Let's shift gears a little bit and talk about sentiment analysis. So sentiment analysis is calculating the sort of emotional or subjective impact of some text. And so in its simplest form, you might be trying to gauge whether someone is saying something positive or negative. So maybe you're going to use this to look at product reviews or movie reviews and try to decide, is someone saying something positive or negative about my product or my movie? Or maybe you can do Twitter analysis of Twitter statements to see whether someone whether people are posting good things about my product or bad things about my product. So the simple and naive approach to sentiment analysis is that you can start with a list of good words and a list of bad words in a lexicon, and you just look for these words or terms in your text, count them up, and maybe that'll tell you what the overall sentiment of a sentence is. So the simple case is, this movie is great. I look and I find great on my list of good words, so I give it a point, and now it looks like that statement is good. Or worst acting I've ever seen, you might find that word worst on your list of negative polarity words, and so that could tell you that that's a negative statement about something. So this is obviously a pretty naive approach, just scoring based on words. So how could we actually improve it, and where does this approach fall short? Well, the obvious thing about it in language is that it's ignoring the context, and it's ignoring the syntactic structure of a sentence where you have some words that are modifying other words. So what if my review was, this movie wasn't bad? Well, there's that bad word. That's on my negative polarity list. But this is actually a positive statement about the movie because I'm negating it. I'm negating the bad word with this movie wasn't because it has the word not in it. So this is how the naive approach sort of falls short. And this suggests that maybe there's an approach that can start with the polarity scoring at the word level, but that can actually add some smarts based on the syntactic structure of a sentence so that I get a more accurate polarity of the sentence when we use something like a negator word. And it turns out there is such an algorithm that works by parsing the sentence first and then looking for patterns in that sentence of negator words composed with negative or positive polarity words. So sentence parsing is where you're taking a sentence and breaking it down into a tree of syntactic components and labeling each one with a part of speech label. So this is an example of that same sentence from the previous slide expressed as a parse tree. And this parse tree was actually generated by the Apache OpenNLP sentence parser, which is a very nice parser. It's open source. And one of the interesting things you can see right away is that the way it tokenized the word wasn't, it actually broke it into two tokens for was and N''T, which is really saying not. And when you see this syntactic structure of that sentence, you can now see that it should be possible for us to parse sentences and then look for patterns in the sentences where we have a positive or negative polarity word and then possibly a negator word that gives us a hint to flip the sign of that polarity. So here's an algorithm that was created by two researchers from Cornell, Choi and Carty. And this algorithm is one they describe in a paper where they lay out 7 rules for compositions of parse components to determine polarity. So if you look at one of these rules, the first one's obvious and the one we looked at, right? If you have the word not, or maybe N''T if it's a contraction, and you have that next to another polarity word, which is either positive or negative, then you should flip the polarity of the overall sentence. Some of the others, if you look at an adjective to a verb, the rule 4, so if you look at the word destroy, destroy might be on your bad list. It might have a negative polarity, but unlikely is a word, it's actually a sort of a content negator word that modifies destroy. So if something is unlikely to destroy the planet, that's just saying a good thing, whereas destroying the planet would be a bad thing. So this is examples of how by picking out negator words and positive and negative polarity words, you can compose them, you can find patterns, and you apply these production rules to actually propagate word-level polarity up to a sentence. And so the rule on the bottom is the compositional rule, where if you match one of these rules, if the first component that you match is a negator, then reverse the polarity of the second argument. Otherwise, go with the polarity of the first argument. So obviously, to do this algorithm, you need several things, right? You need to start with a lexicon of positive and negative polarity words, and also a lexicon of negator words, so you can find them. Sometimes you can find lexicons for what you need already. In this case, SentiWordNet is a popular sentiment analysis lexicon, which is built on top of WordNet, which is the semantic network from Princeton. You can also bootstrap your own polarity lexicon by taking something like WordNet and come up with a list of everything you can think of for positive and negative words, and then hit WordNet and generate all the synonyms of those words and add those to your set, and then repeat. Take all those words and generate synonyms of those, and so you can grow this set of positive and negative words. So this is a way that you can sort of bootstrap your own lexicon, or you can take one off the shelf like SentiWordNet. So this is a very interesting and nice algorithm, and I like it because it combines this sort of simple and statistical approach of just counting words with something like sentence parsing, which actually gets into the syntactic structure of a sentence. So it's a nice interplay between a statistical method and a rule-based method. All right, so how would you put this crazy algorithm on Spark? Once again, you're going to need an NLP pipeline because there's several pre-processing steps you need to do to get in the form where you can actually apply these compositional rules. So I haven't done this. I haven't implemented it in Spark, but this is the way I might approach it, is to think about this as a series of transformations. And you can start maybe at the sentence level for parallelism, right? So if you first apply sentence detection in your pipeline, you have a list of then sentence structures, and then can we take that through a series of transforms where the first transform we apply a parsing algorithm like OpenNLP parse, and you get a parse tree, and then the next transform you look up all of the polarity words and negator words that are going to be at the leaf nodes of your parse tree, and then the next transform apply those compositional rules from the previous slide to propagate the polarity up to the sentence level, and then finally reduce it by document ID to sum up the polarity of each sentence and get an overall polarity score for a document. So that's one way that you might be able to take this algorithm and put it on top of Spark. And once again, your pipeline might need to have several of those components from lower down in the iceberg. So for example, you might want to do word sense disambiguation before you look something up in your polarity lexicon. So as an example, let's take the word concrete. So concrete has one sense as an adjective where it's the opposite of abstract. It's something tangible or something that can be perceived and sensed. And there's also concrete, the noun, which is building material created from cement. So concrete, the adjective, actually has, and if you look in SentiWordNet, they actually give this a positive polarity for the word concrete. But concrete, the building material, neutral, right? So this is an example of if your pipeline does things like word sense disambiguation, you'll get greater precision because when you look up in your lexicon, you can pick the sense of the word accurately, which might have a different polarity score across different senses. So this is, again, an example where a high-level idea or algorithm in NLP is composed of multiple lower-level ideas. And so all the rest of the things you want to do in your pipeline, you have to do sentence parsing, you have to do lexical lookup, you might want to do lemmatization so that your lexicon doesn't have to have every inflection and form of every word. And so you can string these things together in a pipeline. And it would be nice if you could start at the sentence level then and run this as a series of transforms on Spark. So that is sentiment analysis. All right, how are we doing on time? Almost over. So to wrap up, NLP is such a broad field. You know, all those different algorithms and sub-algorithms are each open areas of research. And the great thing about the state of NLP right now is that you can build systems very easily by composing existing libraries across all those different algorithms, which is really nice. And it's really the proliferation of open source software and also the ubiquity of cheap computing that has led to this kind of renaissance in AI and NLP at the moment, where it's almost like building a mashup. You can take this tokenizer and this sentence parser and this lexicon and string them together and actually build an NLP system out of it quite easily. So NLP is really fun, And you also have the satisfaction, if you've built an NLP system, sometimes you get a real kick out of it because it might actually look like it's displaying some intelligent behavior. So this is one of the reasons why I think NLP is such a cool area. It's fun to see results in it. If you have other questions, feel free to send me an email. Anything else? Thank you.